Imagine looking up at the night sky billions of years ago and seeing two neighboring worlds, each cradling oceans, volcanoes, drifting clouds, and rivers that wound their way slowly toward distant seas. One of these worlds became Earth, a planet teeming with life, its surface transformed again and again by the quiet persistence of water and time. The other became Mars, a cold, silent desert, its rivers long since vanished, its skies stripped of the thick blue atmosphere it may once have had. This is the story of that second world, and of the delicate, fragile turn of events that separated its fate so completely from our own. There is something quietly haunting about Mars, something that sets it apart from every other planet in our solar system. It is not simply distant, nor simply barren. It is familiar in a way that unsettles as much as it fascinates. Of all the worlds orbiting our sun, Mars alone seems to whisper of a past that might have run parallel to our own. A planet that, for a brief and extraordinary window in its youth, may have possessed nearly everything Earth possesses today. Liquid water, a thicker atmosphere, a warmer climate, perhaps even the basic ingredients necessary for life to take hold. This is why Mars has captivated human imagination for longer, and more deeply, than any other planet. Ancient civilizations tracked its reddish glow across the night sky, naming it after gods of war for the blood-red color visible even to the naked eye. Centuries later, early telescopic observers debated the existence of canals etched across its surface, imagining a dying civilization desperately channeling water across a parched world. Science fiction writers built entire imagined histories around Martian deserts and lost Martian oceans, and generations of scientists have quietly wondered whether this small, cold planet might hold the answer to one of humanity's oldest questions. Are we alone in the universe? Or did life, in some form, arise there too, only to fade away long before we ever learned to look for it? What makes Mars so uniquely compelling is not simply the possibility of life, but the deeper, more unsettling question that lies just beneath it. Mars and Earth did not begin as vastly different worlds. They were born from the same swirling disk of gas and dust that gave rise to our entire solar system, shaped by the same physical laws, exposed in their earliest years to remarkably similar conditions. Both were rocky planets. Both likely possessed early atmospheres capable of trapping heat. Both, according to a growing body of scientific evidence, once had liquid water flowing freely across their surfaces, carving valleys, filling basins, and perhaps pooling into ancient seas. For a window of time early in the solar system's history, the differences between Earth and Mars may have been far smaller than the vast gulf that separates them today. And yet, somewhere along the way, these two worlds diverged completely. Earth became a living planet, its oceans still full, its atmosphere still thick and protective, its surface still shaped by the same rivers, rains, and tectonic forces that first appeared billions of years ago. Mars became something else entirely. A cold, dry world with an atmosphere so thin that liquid water can no longer exist stably on its surface. Its ancient rivers reduced to dry, dust-filled channels, its once thicker air stripped away into the emptiness of space. The question of exactly why this happened, and exactly when, sits at the very heart of everything we understand, and everything we still do not understand about Mars. This question carries a weight that extends far beyond simple planetary curiosity. If Mars truly once resembled early Earth, and if it later lost the very qualities that make a planet capable of sustaining life, then understanding Mars becomes something more than an exercise in studying a distant neighbor. It becomes a way of understanding our own planet's fragility, a reminder that the conditions allowing life to flourish are not guaranteed, not permanent, and not necessarily unique to Earth alone. Somewhere in Mars's transformation from a warmer, wetter world into the frozen desert we observe today lies a lesson about the delicate balance that has allowed our own planet to remain alive and thriving for billions of years. A balance that Mars, for reasons scientists are still working to fully understand, was ultimately unable to maintain. Modern exploration has only deepened this sense of mystery rather than resolving it. Decades of orbiters, landers, and rovers have sent back evidence that continues to reshape our understanding of Mars's ancient past. Dry riverbeds, carved with the unmistakable signature of flowing water, wind across regions of the Martian surface. Mineral deposits, the kind that only form in the presence of standing water, have been discovered in numerous locations, offering geological proof that liquid water did not simply pass briefly across this planet, but persisted in some form for a significant period in its early history. Some regions of the northern hemisphere show geological features that many scientists interpret as the ancient shoreline of an enormous ocean, one that may have covered as much as a third of the planet's entire surface, billions of years ago. Each of these discoveries adds another small piece to a much larger puzzle, one that scientists have been carefully assembling for decades, drawing on data gathered from an ever-growing fleet of robotic explorers sent to study this distant world in increasingly precise detail. And yet, for every question these missions have answered, several new ones seem to emerge in its place. Why did Mars, a planet seemingly so similar to early Earth, lose its water so completely? What happened to the thicker atmosphere that must once have kept that water stable on the surface? And could any trace of ancient Martian life, if it ever existed at all, have somehow survived the planet's long, slow transformation into the barren world we observe today? These are not simple questions, and they do not have simple answers. They require us to travel back across billions of years, to the very earliest moments of Mars's formation, tracing the planet's history step by step through each dramatic transformation that ultimately led to the cold, quiet world visible in our night sky today. It is a journey that begins not with rivers or oceans, but with the same violent, chaotic birth that shaped every planet in our solar system, Mars included. To understand what Mars became, we first need to return to its birth. To understand how Mars came to exist at all, we must travel back roughly 4.5 billion years, to a time before either Earth or Mars had fully taken shape, back to the swirling, chaotic disk of gas and dust that surrounded our young, newly forming sun. This vast disk, spinning slowly in the darkness of early space, contained within it every ingredient that would eventually become the planets, moons, and countless smaller bodies of our solar system, Mars and Earth included. In the earliest stages of this process, countless microscopic grains of dust and ice, scattered throughout the disk, began to collide and stick together, drawn slowly closer by the gentle pull of gravity. Over time, these small clumps grew into larger fragments, then into boulders, and eventually into what astronomers call planetesimals, small rocky bodies ranging from a few kilometers to several hundred kilometers across. Within the inner regions of this disk, closer to the sun's growing warmth, temperatures were too high for ice and other volatile compounds to remain solid, meaning the planetesimals that formed here, including those that would eventually build both Earth and Mars, were composed predominantly of rock and metal rather than ice. Through countless collisions, spanning millions of years, these planetesimals gradually merged into larger and larger bodies, a slow, violent process of accumulation that scientists refer to as accretion. Each collision released tremendous energy, generating enough heat to keep these growing worlds partially molten during their formative years, allowing heavier elements like iron and nickel to sink toward their centers while lighter rocky material rose toward the surface, a process that shaped the layered internal structure both Earth and Mars still possess today. Mars itself likely formed relatively quickly compared to Earth, reaching roughly half its final size within just a few million years, a surprisingly short timescale in the context of planetary formation. Some scientists believe Mars may have essentially stopped growing early on, its formation cut short by the powerful gravitational influence of nearby Jupiter, whose immense mass likely disrupted the surrounding disk of material before Mars could grow to a size comparable to Earth or Venus. This early interruption may explain why Mars remains considerably smaller than Earth today, despite forming from broadly similar material under broadly similar conditions. The young solar system these newly forming planets inhabited was an environment defined by chaos and relentless bombardment. Countless smaller bodies, debris left over from the planet formation process, continued colliding with the young planets long after their initial formation, a violent period scientists refer to as the late heavy bombardment. During this era, both Earth and Mars would have experienced intense, repeated impacts from asteroids and comets, some large enough to reshape entire regions of their surfaces in a single catastrophic collision. Evidence of this ancient bombardment remains clearly visible on Mars today, preserved across its heavily cratered southern highlands in a way that has long since been erased from Earth's surface through billions of years of erosion, volcanic activity, and plate tectonics. Despite this violence, this same period of intense bombardment may have played a crucial role in delivering essential materials to both young planets. Many scientists believe that a significant portion of Earth's water arrived via collisions with icy comets and water-rich asteroids during this early, chaotic period. Material originally formed in the colder, outer regions of the solar system before being scattered inward through gravitational interactions with the giant planets. Mars, positioned farther from the Sun than Earth, may have received an even greater proportion of its early water through similar means, along with water potentially incorporated directly into the planet during its initial formation from ice-bearing material within the surrounding disk. As both planets gradually settled following this bombardment, their interiors continued generating tremendous heat, driven partly by leftover energy from their violent formation, and partly by the decay of radioactive elements trapped within their rocky material. This internal heat powered extensive volcanic activity across both worlds, releasing gases trapped deep within their interiors up through the surface and into the surrounding space, gradually building the first true atmospheres either planet would possess. On Mars specifically, this early volcanic activity appears to have been extraordinarily intense, releasing significant quantities of carbon dioxide, water vapor, and other gases capable of trapping heat, potentially creating a genuine greenhouse effect strong enough to keep the young planet considerably warmer than it is today, despite its greater distance from the Sun. This early atmosphere holds tremendous significance for everything that would follow in Mars's history. A sufficiently thick atmosphere, combined with the greenhouse warming it provides, would have allowed temperatures across the Martian surface to climb high enough for liquid water to remain stable, rather than immediately freezing solid or evaporating away into the thin vacuum of space, as tends to happen under the cold, low-pressure conditions found on Mars today. Without this early atmospheric protection, the ancient rivers, lakes, and possible ocean that later evidence suggests once existed on Mars would simply not have been possible. Geological evidence gathered from decades of orbital and surface missions strongly supports the idea that Mars did indeed possess a considerably thicker atmosphere during this early period, an atmosphere capable of supporting the kind of warm, wet conditions its ancient landscape still bears witness to today. Certain minerals discovered scattered across the Martian surface, including specific types of clay and carbonate rock, form only through prolonged exposure to liquid water under a stable, moderately warm climate, offering physical, chemical proof that Mars's ancient atmosphere was fundamentally different from the cold, thin one surrounding the planet in the present day. It is a remarkable thought to sit with. In these earliest chapters of solar system history, Mars and Earth followed strikingly similar paths. Both formed from the same violent, dust-filled disk surrounding our young sun. Both endured the same intense, chaotic bombardment of asteroids and comets. Both generated early atmospheres through extensive volcanic activity, atmospheres thick enough to trap heat and allow liquid water to exist and persist across their surfaces. For a brief moment in the vast unfolding timeline of cosmic history, these two worlds, now separated by such an enormous gulf of difference, may have appeared remarkably alike. For a brief moment in cosmic history, Mars may have looked surprisingly familiar. Somewhere beneath the endless red dust that now defines the Martian landscape lies the unmistakable fingerprint of a very different world, one shaped not by wind and dry erosion, but by the slow, patient movement of flowing water. Scattered across Mars's ancient terrain, particularly within its heavily cratered southern highlands, lie thousands of winding channels, carved gradually into the rock over what scientists believe were thousands, or even millions, of years of sustained water flow. These ancient river valleys bear a striking resemblance to river systems found here on Earth, complete with meandering paths, tributary branches merging gradually into larger channels, and smooth, gradual curves that mirror the way water naturally seeks the path of least resistance across a landscape. This particular pattern of erosion is extremely difficult to explain through any process other than sustained liquid water flow, distinguishing these features clearly from the sharper, more chaotic channels typically carved by sudden floods or other short-lived geological events. Some of the largest of these ancient valley networks stretch for hundreds of kilometers across the Martian surface, their branching patterns suggesting a landscape once shaped by regular rainfall or snowmelt, feeding smaller streams that gradually merged into larger rivers, much as similar systems continue to develop here on Earth today. The sheer scale and complexity of these valley networks strongly suggests that liquid water did not simply flow briefly across Mars in a single dramatic event, but persisted in some form across an extended period during the planet's early history, patient and continuous rather than sudden and fleeting. Perhaps even more compelling than the river valleys themselves are the delta formations discovered at the end of several of these ancient channels. On Earth, deltas form where rivers slow down upon entering larger, calmer bodies of water, such as lakes or oceans, causing the sediment carried along by the flowing water to settle and accumulate into the distinctive fan-shaped deposits we recognize today. Remarkably similar delta formations have been identified at multiple locations across Mars, most famously within Jezero crater, a site so geologically compelling that NASA specifically selected it as the landing site for the Perseverance rover, based largely on the strong likelihood that this ancient delta once fed into a stable, long-lasting lake filling the crater floor. The presence of a delta requires very specific conditions to form. It requires a consistent source of flowing water, a stable body of water for that flow to empty into, and enough time for sediment to gradually accumulate into the layered, fan-shaped structure we observe today. Discovering such a feature on Mars offers powerful evidence that Jezero crater, and likely numerous other locations across the planet, once held genuine, long-lasting lakes, rather than merely brief, temporary pools left behind after a single flooding event. Beyond individual lakes and river systems, some of the most striking evidence gathered from decades of orbital observation points toward something considerably larger, an ancient ocean that may have once covered vast stretches of Mars's northern hemisphere. This idea, often referred to as the Northern Ocean hypothesis, is based largely on the observation that much of Mars's northern lowlands sit at a notably lower elevation than the southern highlands, forming a smooth, relatively flat basin that closely resembles the kind of seafloor topography found beneath Earth's own oceans. Orbital spacecraft have identified what many scientists interpret as ancient shoreline features along the boundary between these northern lowlands and the higher terrain to the south, subtle but consistent changes in elevation that mirror the kind of coastal terracing produced by long-term wave action and changing water levels here on Earth. If this interpretation proves accurate, this ancient Martian ocean may have covered as much as a third of the planet's entire surface, holding a volume of water potentially comparable to the Arctic Ocean here on Earth, an almost unimaginable transformation for a world now defined by dry, rust-colored desert stretching endlessly in every direction. This hypothesis remains a subject of ongoing scientific debate, as definitively proving the past existence of an ocean based solely on orbital imagery presents significant challenges. However, additional evidence gathered from mineral analysis across the proposed ocean floor region has lent further support to the idea, with several rover and orbiter missions identifying mineral deposits consistent with prolonged exposure to standing water across this same expansive area. Speaking of minerals, some of the strongest and most direct evidence for Mars's ancient watery past comes not from the shape of the landscape itself, but from the chemical composition of the rocks scattered across it. Certain minerals, including specific clay compounds and sulfate deposits, form only under very particular conditions, typically requiring prolonged exposure to liquid water over extended periods of time. When rovers like Curiosity and Perseverance analyze rock samples containing these mineral signatures, they are essentially reading a kind of geological diary, one written not in words, but in the slow, patient chemistry of ancient water interacting with Martian rock across countless centuries. Clay minerals discovered across numerous locations on Mars are particularly significant in this regard, as they typically form through the gradual weathering of volcanic rock in the presence of relatively neutral, mild water conditions, similar to the kind of freshwater lakes and rivers found across Earth today. This stands in notable contrast to certain other mineral deposits found in different regions of Mars, sulfate-rich formations that instead suggest a later period of more acidic, evaporating water, hinting that Mars's ancient climate likely shifted gradually over time, transitioning from milder lake and river-filled conditions toward a harsher, more challenging environment as the planet's broader climate began to change. Taken together, this extensive body of evidence, sprawling river valleys, carefully preserved delta formations, potential ancient shorelines, and telltale mineral signatures scattered across the surface, paints a compelling and consistent picture. Mars, for a substantial period early in its history, was very likely a considerably warmer, wetter world than the one we observe today, complete with flowing rivers, standing lakes, and quite possibly a genuine ocean covering much of its northern hemisphere. It was a planet that, in this particular chapter of its long history, may have looked remarkably Earth-like, its landscape shaped by the same fundamental forces of flowing water that continue to define our own planet's surface today. And this naturally leads us toward one of the most profound questions in all of planetary science, a question that has driven decades of Mars exploration and continues to shape mission planning even today. If there was water, could there also have been life? If Mars truly once possessed the warm, wet conditions that its ancient landscape so strongly suggests, then a deeper question naturally follows, one that has shaped the direction of Mars exploration for decades and continues to guide mission planning today. Wherever liquid water persists on Earth, life inevitably seems to find a way to take hold, thriving in environments ranging from deep ocean vents to frozen polar lakes to acidic hot springs. If Mars once offered similar conditions, even for a limited window of time, could life have emerged there as well? This question does not require us to imagine anything as complex as visible plants or animals wandering across an ancient Martian landscape. Scientists searching for evidence of past life on Mars are focused almost entirely on the possibility of microbial life, simple, single-celled organisms similar to the earliest forms of life that appeared on Earth billions of years ago. If conditions on early Mars truly paralleled those on early Earth, as much of the geological evidence suggests, then the basic ingredients necessary for such simple life, liquid water, essential chemical elements, and a stable energy source, may well have been present on both worlds during roughly the same period in their early history. One of the primary tools scientists use in this search involves looking for organic molecules, carbon-based compounds that serve as the fundamental building blocks of life as we understand it. It is important to note that the presence of organic molecules alone does not prove that life once existed, since these compounds can also form through purely non-biological chemical processes. However, discovering organic molecules on Mars remains a significant and necessary step, confirming that at least some of the basic chemical ingredients required for life were indeed present and preserved within the Martian environment. NASA's Curiosity rover, exploring Gale Crater since its landing in 2012, has made several significant discoveries in this regard, identifying complex organic molecules preserved within ancient Martian mudstone, rock formed from fine sediment that once settled at the bottom of a long-lasting lake. The specific complexity and diversity of these organic compounds suggests they were likely preserved through unusually favorable conditions, offering scientists valuable insight into the kind of chemical environment that existed within this ancient lake billions of years ago, an environment that, at least in principle, could have been capable of supporting simple microbial life. Building directly on these discoveries, NASA's Perseverance rover was specifically designed with an even more ambitious goal in mind, actively searching for biosignatures, physical or chemical evidence that would suggest the past presence of life, rather than simply the basic chemical ingredients that life requires. Landing within Jezero Crater in 2021, a location chosen specifically because of its ancient river delta and strong evidence of a long-lasting lake, Perseverance has spent years carefully examining rock formations along the crater floor and its surrounding delta, searching for the kind of subtle textures, chemical patterns, and mineral structures that might indicate ancient biological activity. Among the most promising discoveries made by Perseverance are certain rock formations containing distinctive patterns that some scientists believe could represent biosignatures, though the interpretation of these features remains genuinely uncertain and actively debated within the scientific community. Similar patterns in some cases can form through purely chemical processes without any biological involvement whatsoever, meaning that definitively confirming these features as true evidence of ancient life requires an extremely high standard of scientific verification, one that current rover instruments, however sophisticated, cannot fully provide on their own. This is precisely why Perseverance has been carefully collecting and storing rock samples throughout its mission, sealing them within specialized containers designed to preserve their exact chemical and physical properties, in preparation for an ambitious future mission known as Mars Sample Return. This planned mission would involve retrieving these carefully collected samples and transporting them back to Earth, where scientists could study them using the full range of sophisticated laboratory equipment available here, far more advanced and varied than anything that could realistically be transported to Mars aboard a rover. Only through this kind of detailed, Earth-based analysis could scientists hope to definitively confirm or rule out the presence of ancient biosignatures within these carefully preserved Martian samples. The search for ancient life on Mars extends beyond simply searching for direct biological evidence within the rocks themselves. Scientists must also carefully consider the broader environmental conditions that would have needed to exist in order for life to survive and persist across any meaningful span of time. This includes evaluating the chemical composition of ancient lakebeds for essential nutrients, assessing how stable and long-lasting these watery environments likely remained, and considering whether Mars's ancient atmosphere provided sufficient protection from harmful solar radiation, a factor that becomes increasingly significant as we consider the later chapters of the planet's history. It is worth pausing to consider just how remarkable this entire search truly is. Scientists are not simply looking for life on a distant, alien world in the present day. They are searching for faint, billions-year-old evidence of life that may have existed only briefly, within a narrow window of favorable conditions, on a planet that has since transformed dramatically into the cold, dry desert we observe today. It is an extraordinarily delicate scientific pursuit, akin to searching for a handful of specific grains of sand scattered somewhere across an entire beach, using tools capable of examining only a tiny handful of that sand at any given time. Despite these significant challenges, the scientific motivation driving this search remains extraordinarily strong, precisely because of what confirming ancient Martian life would mean for our broader understanding of the universe. If life once existed on Mars, entirely independent from life on Earth, it would suggest that the emergence of life may not be a rare, singular event unique to our own planet, but rather a natural, perhaps even common outcome whenever the right conditions align elsewhere in the universe. Such a discovery would fundamentally reshape our understanding of our own significance within the cosmos, transforming Mars from a quiet, distant neighbor into powerful evidence that life itself may be far more common throughout the universe than we have ever been able to confirm. Yet for all this hopeful searching, for all the careful examination of ancient lakebeds and preserved organic molecules, the story of Mars's habitability was destined to change dramatically. Whatever conditions may have allowed simple life to potentially take hold during this early, water-rich period would not last indefinitely. Deep within the planet itself, a slow, irreversible process was already underway, one that would eventually strip away the very atmosphere and protection that made Mars's ancient rivers and lakes possible in the first place. Yet life would face a growing problem. Deep beneath the ancient lakebeds and dry river valleys we have explored so far, far below the reach of any rover or orbiter, lies the true origin point of Mars's transformation from a warm, wet world into the cold desert we observe today. To understand this transformation, we must look not at the planet's surface, but at its core, and at an invisible, protective force that Mars once possessed, much like Earth still does, but which it gradually and permanently lost. Every rocky planet forms with a molten interior, generated by the immense heat produced during its violent formation and sustained afterward by the slow decay of radioactive elements trapped within its rocky material. In Mars's earliest history, this molten interior included a liquid metallic core, likely composed primarily of iron mixed with smaller amounts of lighter elements such as sulfur. As this molten iron core churned and circulated within the young planet, it generated a global magnetic field, an invisible but powerful force extending far out into space, surrounding the entire planet in a protective magnetic bubble, similar in concept to the magnetic field that continues to surround Earth today. This magnetic field, though invisible, would have played an absolutely essential role in Mars's early habitability. On Earth, our own magnetic field serves as a crucial shield, deflecting the constant stream of charged particles flowing outward from the Sun, a phenomenon known as the solar wind. Without this protective magnetic shield, these charged particles would gradually strip away lighter atmospheric molecules over time, slowly eroding a planet's atmosphere into the vacuum of space. Mars's early magnetic field is believed to have provided this same essential protection, shielding the planet's thick, early atmosphere long enough to allow the warm, water-rich conditions we explored in earlier chapters to persist and stabilize. However, unlike Earth, whose core has remained active and molten for over 4 billion years, Mars's significantly smaller size worked against it in this regard. Because Mars is considerably smaller than Earth, containing less total mass, and therefore generating comparatively less internal heat, its core began cooling and solidifying far more rapidly than Earth's has. As Mars's core gradually cooled, the churning, circulating motion of molten metal responsible for generating its magnetic field began to slow, and eventually, sometime within the first billion years of the planet's history, this internal dynamo process stopped entirely. The consequences of this loss extended far beyond the interior of the planet itself. Without a functioning magnetic field to deflect it, the solar wind, that constant stream of charged particles flowing outward from the Sun, began interacting directly with Mars's upper atmosphere for the first time. Rather than being safely deflected around the planet as occurs on Earth, these charged particles instead began colliding directly with atmospheric molecules, gradually knocking them loose from Mars's gravitational hold and carrying them off into space, a slow, continuous process of atmospheric erosion that would ultimately reshape the entire character of the planet. Much of what scientists currently understand about this critical process comes from NASA's MAVEN mission, launched specifically to study how Mars's atmosphere continues interacting with the solar wind in the present day. Arriving at Mars in 2014, MAVEN has spent years directly measuring the rate at which solar wind particles continue stripping away small amounts of Mars's remaining atmosphere, even now, billions of years after the planet's magnetic field first collapsed. These ongoing measurements have allowed scientists to calculate, with reasonable confidence, how quickly this same erosion process likely occurred throughout Mars's ancient past, providing crucial data for understanding the broader timeline of the planet's transformation. MAVEN's observations have revealed that atmospheric loss driven by the solar wind, while relatively gradual under current conditions, would have occurred considerably more rapidly during Mars's early history, particularly during a period when our young sun was significantly more active than it is today. Young stars, including our own sun in its early history, tend to produce considerably stronger stellar winds and more frequent, intense bursts of radiation compared to their more settled, middle-aged state. This means that early Mars, having just lost the protective magnetic field that once shielded it, would have been exposed to an unusually intense period of atmospheric stripping, precisely during the same era when our sun was at its most volatile and energetic. It is worth pausing here to appreciate just how significant Earth's own magnetic field truly is, particularly in light of everything Mars's history reveals. Earth's magnetic field is generated by our planet's much larger, still molten outer core, a churning layer of liquid iron and nickel that has remained active for over 4 billion years, continuously generating the protective magnetic bubble that surrounds our entire planet today. This magnetic field does far more than simply create the beautiful auroras visible near Earth's polar regions. It serves as an essential ongoing shield, protecting our atmosphere, and by extension, all life on Earth, from the same kind of solar wind erosion that gradually stripped away Mars's atmosphere billions of years ago. In many ways, Mars offers us a sobering glimpse of what Earth's own fate might have eventually resembled, had our planet been smaller, had our core cooled more quickly, or had our magnetic field collapsed in the same way Mars's did so long ago. It is a humbling realization, understanding that something as invisible and seemingly abstract as a planet's internal magnetic field can ultimately determine whether that world remains capable of supporting liquid water and life, or gradually transforms into a cold, dry desert stripped of its protective atmosphere. As Mars's magnetic field faded, and the solar wind began its slow, patient work of stripping away the planet's atmosphere, the thick, warm conditions that had once allowed rivers to flow and lakes to form began to change as well. With less atmosphere available to trap heat and maintain stable surface pressure, temperatures across the planet gradually began to fall, and the delicate conditions required for liquid water to remain stable on the surface slowly began to disappear. This was not a sudden, dramatic event, but rather a slow, almost imperceptible transformation, unfolding gradually across hundreds of millions of years, as Mars steadily lost the very qualities that had once made it appear so remarkably similar to early Earth. Without its invisible shield, Mars slowly began to die. There is no single moment that marks the death of a planet, no sudden catastrophe, no dramatic collapse visible from a distance. Mars's transformation from a warm, water-rich world into the cold desert we observe today unfolded instead across an almost incomprehensible span of time, a slow, patient unraveling that stretched across hundreds of millions of years, each small change building quietly upon the last until the planet had been utterly and permanently reshaped. With Mars's magnetic field gone, and the solar wind steadily stripping away atmospheric molecules into the surrounding vacuum of space, the planet's atmosphere grew gradually thinner with each passing millennium. This slow but continuous loss carried significant consequences for the broader Martian climate, since atmospheric density plays a crucial role in regulating a planet's surface temperature and pressure. As Mars's atmosphere thinned, its capacity to trap heat through the greenhouse effect diminished correspondingly, causing average surface temperatures across the planet to gradually decline. This cooling climate set in motion a slow, self-reinforcing cycle that would ultimately transform the entire character of the planet. As temperatures fell, water that had once flowed freely across the Martian surface began to freeze more readily, gradually locking away what had once been rivers, lakes, and quite possibly an entire ocean, into ice rather than liquid form. With less liquid water actively cycling through the Martian atmosphere via evaporation, rainfall grew increasingly rare, further starving the remaining rivers and lakes of the replenishment they needed to persist, causing them to shrink, stagnate, and eventually disappear entirely across most of the planet's surface. Simultaneously, as atmospheric pressure continued to decline alongside this cooling process, Mars approached and eventually crossed a critical physical threshold, a point at which the atmospheric pressure across most of the planet's surface became too low for liquid water to remain stable at all, regardless of temperature. Below this threshold, water exposed to the Martian surface no longer melts into liquid form the way ice does here on Earth. Instead, it transitions directly from solid ice into water vapor, a process called sublimation, skipping the liquid phase entirely. This fundamental shift in the basic physics governing water on Mars's surface marked an essentially irreversible turning point in the planet's transformation, one that persists to this very day. As Mars's remaining surface water either froze permanently or gradually sublimated away into the thin atmosphere above, much of it eventually migrated toward the planet's polar regions, where it accumulated into the large ice caps that remain clearly visible at Mars's north and south poles today. These polar ice caps, composed of a combination of frozen water and frozen carbon dioxide, essentially dry ice, represent some of the last significant reservoirs of Mars's ancient water, locked permanently away in a form no longer capable of flowing freely across the planet's surface, as it once did billions of years earlier. Beyond the freezing and sublimation of surface water, Mars's declining atmosphere likely triggered additional significant changes to the planet's carbon dioxide cycle as well. Earlier in Mars's history, evidence suggests the planet's atmosphere contained substantially more carbon dioxide than it does today, a key ingredient in generating the greenhouse warming necessary to sustain a warmer early climate. As the planet's atmosphere thinned and temperatures continued falling, much of this carbon dioxide likely became trapped within surface rocks and polar ice, further reducing the atmosphere's capacity for greenhouse warming and accelerating the planet's gradual cooling even further in a slow, compounding cycle that continued reshaping Mars across hundreds of millions of years. As Mars's climate grew progressively colder and drier, the landscape itself began transforming correspondingly. The ancient river valleys and lake beds we explored earlier, once active and flowing, gradually dried out completely, leaving behind only the fossilized outlines of their former selves, silent channels and empty basins carved into rock that would remain largely unchanged for billions of years afterward, preserved almost perfectly by the very dryness that had ended their original purpose. Winds, no longer softened by moisture in the atmosphere, began sweeping loose sediment and fine dust across the planet's surface with increasing frequency, gradually burying and reshaping the landscape into the endless, rust-colored deserts that define Mars's appearance today. This distinctive rust-colored appearance, so recognizable and so central to Mars's identity as the red planet, is itself a direct consequence of this long transformation. The reddish hue covering much of the Martian surface comes from iron oxide, essentially a form of rust, formed through a slow chemical reaction between iron-rich minerals in the Martian soil and the small amounts of oxygen and moisture present in the ancient atmosphere. This oxidation process, unfolding gradually across billions of years, quite literally rusted the surface of an entire planet, transforming what may have once been a more neutral, rocky landscape into the deep red deserts so instantly recognizable in every image captured of Mars today. By the time this long transformation had fully run its course, roughly 3 to 4 billion years ago, according to most current scientific estimates, Mars had become fundamentally unrecognizable compared to the warmer, wetter world it had been in its earliest history. Its rivers had dried into empty channels. Its ancient ocean, if it truly existed as current evidence increasingly suggests, had either frozen away or gradually escaped into space, carried off molecule by molecule through the same slow atmospheric stripping process that continues at a reduced pace even today. Its thick, early atmosphere had thinned dramatically, leaving behind only a fraction of its original density, far too little to support liquid water or meaningful greenhouse warming across the planet's surface any longer. What remained was the Mars we recognize today, a cold, dry, thin-atmosphered world of rust-colored deserts, frozen polar ice caps, and ancient, silent riverbeds, a planet whose surface still bears the unmistakable fingerprints of its former life as a warmer, wetter world, even though that world itself vanished long before anything resembling complex life had the opportunity to fully emerge and flourish there. And yet, despite this profound transformation, despite losing its water, its thick atmosphere, and its protective magnetic field, Mars did not become entirely still. Deep beneath its cold, dry surface, tremendous geological forces remained at work, forces that would eventually give rise to some of the most extraordinary and dramatic landscape features found anywhere in our entire solar system. Yet Mars refused to become completely silent. Deep beneath the ancient lake beds and dry river valleys we have explored so far, far below the reach of any rover or orbiter, lies the true origin point of Mars's transformation from a warm, wet world into the cold desert we observe today. To understand this transformation, we must look not at the planet's surface, but at its core, and at an invisible, protective force that Mars once possessed, much like Earth still does, but which it gradually and permanently lost. Every rocky planet forms with a molten interior, generated by the immense heat produced during its violent formation, and sustained afterward by the slow decay of radioactive elements trapped within its rocky material. In Mars's earliest history, this molten interior included a liquid metallic core, likely composed primarily of iron mixed with smaller amounts of lighter elements such as sulfur. As this molten iron core churned and circulated within the young planet, it generated a global magnetic field, an invisible but powerful force extending far out into space, surrounding the entire planet in a protective magnetic bubble, similar in concept to the magnetic field that continues to surround Earth today. This magnetic field, though invisible, would have played an absolutely essential role in Mars's early habitability. On Earth, our own magnetic field serves as a crucial shield, deflecting the constant stream of charged particles flowing outward from the sun, a phenomenon known as the solar wind. Without this protective magnetic shield, these charged particles would gradually strip away lighter atmospheric molecules over time, slowly eroding a planet's atmosphere into the vacuum of space. Mars's early magnetic field is believed to have provided this same essential protection, shielding the planet's thick, early atmosphere long enough to allow the warm, water-rich conditions we explored in earlier chapters to persist and stabilize. However, unlike Earth, whose core has remained active and molten for over 4 billion years, Mars's significantly smaller size worked against it in this regard. Because Mars is considerably smaller than Earth, containing less total mass, and therefore generating comparatively less internal heat, its core began cooling and solidifying far more rapidly than Earth's has. As Mars's core gradually cooled, the churning, circulating motion of molten metal responsible for generating its magnetic field began to slow, and eventually, sometime within the first billion years of the planet's history, this internal dynamo process stopped entirely. The consequences of this loss extended far beyond the interior of the planet itself. Without a functioning magnetic field to deflect it, the solar wind, that constant stream of charged particles flowing outward from the sun, began interacting directly with Mars's upper atmosphere for the first time. Rather than being safely deflected around the planet as occurs on Earth, these charged particles instead began colliding directly with atmospheric molecules, gradually knocking them loose from Mars's gravitational hold and carrying them off into space, a slow, continuous process of atmospheric erosion that would ultimately reshape the entire character of the planet. Much of what scientists currently understand about this critical process comes from NASA's MAVEN mission, launched specifically to study how Mars's atmosphere continues interacting with the solar wind in the present day. Arriving at Mars in 2014, MAVEN has spent years directly measuring the rate at which solar wind particles continue stripping away small amounts of Mars's remaining atmosphere, even now, billions of years after the planet's magnetic field first collapsed. These ongoing measurements have allowed scientists to calculate, with reasonable confidence, how quickly this same erosion process likely occurred throughout Mars's ancient past, providing crucial data for understanding the broader timeline of the planet's transformation. MAVEN's observations have revealed that atmospheric loss driven by the solar wind, while relatively gradual under current conditions, would have occurred considerably more rapidly during Mars's early history, particularly during a period when our young sun was significantly more active than it is today. Young stars, including our own sun in its early history, tend to produce considerably stronger stellar winds and more frequent, intense bursts of radiation compared to their more settled, middle-aged state. This means that early Mars, having just lost the protective magnetic field that once shielded it, would have been exposed to an unusually intense period of atmospheric stripping, precisely during the same era when our sun was at its most volatile and energetic. It is worth pausing here to appreciate just how significant Earth's own magnetic field truly is, particularly in light of everything Mars's history reveals. Earth's magnetic field is generated by our planet's much larger, still molten outer core, a churning layer of liquid iron and nickel that has remained active for over 4 billion years, continuously generating the protective magnetic bubble that surrounds our entire planet today. This magnetic field does far more than simply create the beautiful auroras visible near Earth's polar regions. It serves as an essential ongoing shield, protecting our atmosphere, and by extension, all life on Earth, from the same kind of solar wind erosion that gradually stripped away Mars's atmosphere billions of years ago. In many ways, Mars offers us a sobering glimpse of what Earth's own fate might have eventually resembled, had our planet been smaller, had our core cooled more quickly, or had our magnetic field collapsed in the same way Mars's did so long ago. It is a humbling realization, understanding that something as invisible and seemingly abstract as a planet's internal magnetic field can ultimately determine whether that world remains capable of supporting liquid water and life, or gradually transforms into a cold, dry desert stripped of its protective atmosphere. As Mars's magnetic field faded, and the solar wind began its slow, patient work of stripping away the planet's atmosphere, the thick, warm conditions that had once allowed rivers to flow and lakes to form began to change as well. With less atmosphere available to trap heat and maintain stable surface pressure, temperatures across the planet gradually began to fall, and the delicate conditions required for liquid water to remain stable on the surface slowly began to disappear. This was not a sudden, dramatic event, but rather a slow, almost imperceptible transformation, unfolding gradually across hundreds of millions of years, as Mars steadily lost the very qualities that had once made it appear so remarkably similar to early Earth. Without its invisible shield, Mars slowly began to die. If Olympus Mons represents the towering, vertical extreme of Martian geology, then Valles Marineris represents its precise opposite, an almost unimaginably vast wound cut deep into the planet's surface, stretching so far across the Martian landscape that it would span nearly the entire width of the continental United States if placed upon Earth's own surface. Valles Marineris extends for approximately 4,000 kilometers, roughly 1/5 of the entire circumference of Mars itself, making it, by a considerable margin, the longest canyon system found anywhere in our solar system. At certain points along its length, this immense canyon system reaches depths of up to 7 kilometers, more than 7 times deeper than Earth's own Grand Canyon, and widths reaching nearly 200 kilometers across, wide enough that an observer standing at the canyon's rim in certain locations would be entirely unable to see the opposite wall, lost far beyond the natural curvature of the Martian horizon itself. To put this staggering scale into a more familiar comparison, if Valles Marineris were somehow transplanted onto Earth's surface, positioned across the continental United States, this single canyon system would stretch from the eastern seaboard all the way to the Pacific coastline, a single, continuous geological feature spanning almost the entire width of the country. Earth's own Grand Canyon, by contrast, despite its own considerable grandeur and significance, would appear as little more than a minor side branch when placed alongside the true scale of its Martian counterpart. Given its immense size, it would be reasonable to assume that Valles Marineris formed through the same basic process responsible for creating the Grand Canyon here on Earth, the slow, patient erosion of flowing water carving gradually through rock across millions of years. However, the true origin of this vast Martian canyon system tells a very different geological story, one connected closely to the same powerful volcanic forces responsible for building Olympus Mons and the broader Tharsis region we explored in the previous chapter. Scientists believe Valles Marineris formed primarily through tectonic activity, specifically through a process of crustal stretching and fracturing that occurred as the Tharsis region gradually bulged upward under the tremendous pressure of rising volcanic material deep beneath the surface. As this massive volcanic plateau grew and swelled outward over hundreds of millions of years, the surrounding Martian crust was placed under tremendous physical strain, eventually causing it to crack and fracture along a series of massive fault lines, creating the initial, deep rifts that would eventually widen and deepen into the canyon system we observe today. This origin story stands in notable contrast to Earth's Grand Canyon, formed almost entirely through the patient, gradual erosion of the Colorado River carving downward through rock over millions of years. Valles Marineris, by comparison, began not through erosion, but through the raw, powerful mechanics of a planet's crust literally being stretched and torn apart by the immense geological forces generated deep within its interior, a process closely tied to the same volcanic activity responsible for building the largest mountain in the entire solar system, just a relatively short distance away. This does not mean, however, that water played no role whatsoever in shaping Valles Marineris throughout its long geological history. Evidence gathered from orbital imaging suggests that after these initial tectonic rifts formed, water, potentially including flash floods generated by melting ice or underground water sources breaking through to the surface, may have subsequently flowed through portions of the canyon system, gradually widening certain sections and carving additional smaller channels into the canyon's walls and floor. This suggests that Valles Marineris likely experienced a complex, multi-stage formation process, beginning with the powerful tectonic forces generated by the nearby Tharsis Bulge, followed by a subsequent period of water-related erosion that helped further shape and refine the canyon's final appearance. Alongside this combination of tectonic and water-related shaping, Valles Marineris has also been significantly influenced by massive landslides throughout its long history, some of the largest such events ever identified anywhere in the solar system. The canyon's extraordinarily steep walls, in certain sections rising several kilometers almost vertically from the canyon floor below, have proven susceptible to periodic collapse, sending enormous volumes of rock and debris cascading downward in landslides so large that their resulting debris fields remain clearly visible from orbit even today, spreading for tens of kilometers across the canyon floor in some locations. Beyond its sheer scale and dramatic geological history, Valles Marineris holds particular significance for scientists studying Mars's broader climate history, given that its immense depth exposes multiple distinct layers of rock, each representing a different chapter in the planet's long geological past. By carefully studying the exposed rock layers visible along the canyon's steep walls, scientists can examine a kind of natural cross-section through billions of years of Martian history, comparable in principle to how geologists on Earth study exposed rock layers within our own canyons and cliff faces to reconstruct ancient climate and geological conditions. This layered structure has made Valles Marineris a location of significant ongoing scientific interest, as future missions specifically designed to explore portions of the canyon system could potentially provide scientists with unprecedented access to distinct geological time periods. All conveniently exposed within relatively close proximity to one another along the canyon's dramatic walls, rather than requiring separate missions to entirely different regions of the planet to achieve the same broader understanding of Mars's long, complex geological history. Despite decades of orbital study, Valles Marineris remains a location that no rover or lander has ever directly explored, its extraordinarily steep terrain and challenging topography presenting significant engineering obstacles for any potential landing mission. This means that, much like many other regions of Mars we have already explored throughout this documentary, our current understanding of Valles Marineris remains based primarily on orbital observation, careful and detailed, but still fundamentally limited compared to the kind of direct, close-up examination only a dedicated surface mission could ultimately provide. The surface isn't the only place hiding secrets. For all that Mars reveals across its dramatic surface, its towering volcanoes, its vast canyon systems, its dry, ancient riverbeds stretching endlessly across the landscape, some of the planet's most compelling secrets remain hidden entirely from view, buried beneath the surface in regions no camera has ever directly photographed and no rover has yet fully explored. Among the most significant of these hidden features is underground ice, vast reserves of frozen water believed to exist just beneath the Martian surface across numerous regions of the planet, particularly toward its middle latitudes, positioned between the permanently frozen polar ice caps and the warmer, drier regions closer to the equator. Unlike the visible ice found at Mars's poles, this underground ice remains concealed beneath a protective layer of rocky soil and dust, shielded from the same processes of sublimation that would otherwise cause it to gradually escape into the thin Martian atmosphere above. Evidence for this underground ice has emerged gradually over decades, drawn from multiple independent sources of scientific observation. Orbital instruments capable of detecting hydrogen, an element strongly associated with the presence of water ice, have identified significant concentrations just beneath the surface across broad regions of the Martian mid-latitudes. In several locations, fresh impact craters formed by small meteorite strikes have exposed bright, reflective ice just beneath the surface, briefly visible before gradually fading as the exposed ice slowly sublimates away under direct exposure to the thin Martian atmosphere, offering scientists valuable, if fleeting, direct confirmation of ice hidden just below the surface in these regions. Some of this underground ice appears to exist not as a simple, solid layer, but in the form of buried glaciers, extensive ice formations covered by a protective layer of rocky debris thick enough to have prevented significant sublimation across potentially millions of years. Radar instruments aboard several Mars orbiters have identified what scientists interpret as debris-covered glaciers within numerous locations across the mid-latitude regions, structures that may represent some of the largest and most easily accessible reserves of water ice found anywhere on the Martian surface. A discovery carrying significant implications not only for understanding Mars's climate history, but also for the practical challenges of any future human exploration of the planet, a topic we will return to in a later chapter. Alongside this hidden ice, Mars also harbors an extensive network of lava tubes, long, hollow tunnels formed during the planet's ancient volcanic history, when flowing lava gradually cooled and solidified along its outer surface, while continuing to flow molten through its interior, eventually draining away entirely and leaving behind a long, hollow tunnel carved directly through solid rock. Similar lava tubes exist here on Earth as well, found in volcanic regions including Hawaii and Iceland, though Mars's tubes appear considerably larger, a consequence of the planet's significantly weaker surface gravity, which allows these underground structures to remain structurally stable at a much greater scale than would be possible under Earth's stronger gravitational pull. Orbital imaging has identified numerous locations across Mars, particularly within the same Tharsis volcanic region responsible for Olympus Mons and its neighboring volcanoes, where sections of these lava tubes appear to have partially collapsed, creating deep, circular pits, sometimes called skylights, that offer a rare glimpse into the otherwise hidden tunnels extending below. These skylights have generated considerable scientific interest, not only for what they might reveal about Mars's volcanic history, but also for their potential significance regarding future human exploration of the planet. This potential significance connects directly to one of the most persistent and serious challenges facing any future human presence on Mars, a topic we will explore in far greater detail in an upcoming chapter, namely the planet's almost complete lack of protection from harmful cosmic and solar radiation, a direct consequence of the same magnetic field loss we examined several chapters ago. Lava tubes positioned safely beneath meters of solid volcanic rock could potentially offer natural, pre-existing shelter from this radiation, along with additional protection from the extreme temperature swings and occasional dust storms that characterize the modern Martian surface environment, making them a location of genuine scientific and practical interest for scientists considering the long-term feasibility of future Martian exploration. Beyond ice and lava tubes, Mars's hidden interior has also revealed itself gradually through a very different kind of scientific instrument, one designed not to photograph or scan the subsurface directly, but instead to listen. NASA's InSight lander, which operated on the Martian surface between 2018 and 2022, carried with it a highly sensitive seismometer specifically designed to detect Marsquakes, seismic vibrations traveling through the planet's interior, similar in principle to the seismic instruments used here on Earth to study earthquakes, and by extension, our own planet's internal structure. Over the course of its mission, InSight detected over 1,000 Marsquakes, providing scientists with an unprecedented opportunity to study the planet's deep interior structure by carefully analyzing how these seismic waves traveled through different layers of rock beneath the surface. This data allowed scientists to construct a considerably more detailed picture of Mars's internal structure than had ever been possible before, revealing a core notably larger than many earlier models had predicted, along with a mantle structured somewhat differently from what scientists had previously assumed based on more limited, indirect evidence gathered before InSight's mission began. These seismic discoveries carry particular significance when considered alongside everything we explored regarding Mars's ancient magnetic field several chapters ago. Understanding the precise size, composition, and current state of Mars's core helps scientists refine their broader understanding of exactly when and why the planet's magnetic field first collapsed billions of years ago, adding valuable new data to a scientific question that had, until relatively recently, relied primarily on indirect evidence and theoretical modeling, rather than direct measurement of the planet's actual interior structure. Taken together, these hidden features, buried ice, ancient lava tubes, and a deep interior only recently mapped through the patient science of Marsquark detection, reveal a planet whose secrets extend considerably beyond what any surface photograph could ever fully capture. Mars, for all the extensive study it has already received across decades of orbital and surface exploration, remains a world whose full complexity continues to reveal itself gradually, one careful measurement and one patient scientific instrument at a time. The more we explore Mars, the more mysteries appear. Everything we have explored throughout this documentary, the ancient rivers, the ambiguous hints of past life, the collapsed magnetic field, the towering volcanoes, and the hidden ice and lava tubes buried beneath the surface, exists within our understanding today because of one of the most remarkable, sustained efforts in the entire history of space exploration, a decades-long campaign of robotic missions that have gradually transformed Mars from a faint, mysterious point of light into one of the most thoroughly studied planets beyond Earth itself. This story of exploration began in earnest during the 1970s, with NASA's Viking program, the first mission to successfully land operational spacecraft on the Martian surface. Two identical Viking landers touched down on Mars in 1976, each equipped with cameras and a suite of scientific instruments specifically designed to search directly for signs of biological activity within the Martian soil. While the results of these early biological experiments proved genuinely ambiguous and remain debated among scientists even today, the Viking landers succeeded in capturing humanity's first clear, detailed photographs taken directly from the Martian surface, transforming Mars almost overnight from a distant, telescopic curiosity into a tangible, physically explorable world. Following Viking, over 2 decades would pass before NASA returned successfully to the Martian surface, this time with a considerably more ambitious approach centered around mobile exploration rather than stationary landers. In 2004, twin rovers named Spirit and Opportunity touched down on opposite sides of the planet, each designed for a primary mission lasting only 90 days. Yet both rovers would go on to vastly exceed these initial expectations in ways that genuinely surprised even the scientists and engineers who built them. Spirit continued operating for over 6 years before finally becoming stuck in soft Martian soil, while Opportunity achieved an almost unbelievable operational lifespan of nearly 15 years, traveling a total distance of over 45 kilometers across the Martian surface before a massive planet-wide dust storm in 2018 finally ended its historic mission. Together, these two rovers provided extensive direct evidence of Mars's ancient watery past, identifying mineral formations and geological features across numerous locations that offered some of the earliest, most compelling confirmation that liquid water had indeed once flowed and pooled across the Martian surface in its ancient history. Building upon the success of Spirit and Opportunity, NASA's Curiosity rover arrived at Mars in 2012, representing a significant leap forward in both scientific capability and technological sophistication. Considerably larger than its predecessors, roughly the size of a small car, Curiosity carried a substantially more advanced suite of scientific instruments, including tools capable of directly analyzing the chemical composition of Martian rock and soil samples. Landing within Gale Crater, specifically chosen due to strong orbital evidence suggesting the presence of an ancient lakebed, Curiosity has spent well over a decade gradually climbing the lower slopes of Mount Sharp, a large mountain rising from the crater's center, carefully examining countless layers of ancient rock along the way, each layer representing a distinct chapter in the region's long geological and climatic history. Curiosity's discoveries throughout this extended mission have proven remarkably significant, including the identification of complex organic molecules preserved within ancient mudstone, along with detailed chemical evidence confirming that Gale Crater once held a long-lasting lake environment, quite possibly stable enough to have supported simple microbial life, had such life existed on Mars during the same period of the planet's ancient history. More recently, NASA's Perseverance rover, which we explored in greater detail during our earlier discussion of the search for ancient Martian life, arrived at Jezero Crater in 2021, carrying with it not only an advanced suite of scientific instruments, but also a small technological companion that would go on to make history entirely on its own. Ingenuity, a small experimental helicopter attached to Perseverance's underside during the journey to Mars, successfully completed the first-ever powered, controlled flight on another planet in April of 2021, a remarkable technical achievement given the extraordinarily thin Martian atmosphere, only about 1% as dense as Earth's own atmosphere, presenting enormous engineering challenges for generating sufficient aerodynamic lift. Ingenuity's initial flight plan called for only a handful of short test flights across a mission, lasting roughly a month. Instead, much like Spirit and Opportunity decades earlier, Ingenuity vastly exceeded these initial expectations, ultimately completing over 70 successful flights across nearly 3 years of continuous operation, providing valuable aerial imagery and demonstrating conclusively that powered flight, once considered nearly impossible within Mars's extraordinarily thin atmosphere, could indeed become a genuinely useful tool for future Martian exploration. Perseverance itself continues operating today, methodically exploring Jezero Crater's ancient river delta, while carefully collecting and sealing rock samples in specialized containers, samples specifically selected based on their strong potential to contain preserved biosignatures or other scientifically significant evidence regarding the crater's ancient watery past. These carefully collected samples currently remain on Mars, awaiting retrieval through NASA's planned Mars Sample Return mission, an ambitious multi-spacecraft effort designed to finally bring physical samples of Martian rock back to Earth for the first time in human history, allowing scientists to study them using laboratory equipment far more sophisticated and varied than anything currently possible to transport directly to the Martian surface. This planned sample return mission represents a significant and complex undertaking, requiring multiple separate spacecraft working in careful coordination, including a dedicated lander to retrieve Perseverance's collected samples, a small rocket capable of launching those samples directly from the Martian surface into orbit, and an additional spacecraft to capture this sample container in orbit before finally beginning the long journey back toward Earth. While the exact timeline and specific mission architecture continue to be refined and adjusted based on budgetary and technical considerations, this ambitious effort represents one of the most significant and consequential planned achievements in the ongoing history of Mars exploration, a potential turning point that could finally provide definitive answers to many of the questions we have explored throughout this documentary. Considered together, this remarkable sequence of missions, spanning from Viking's first tentative landing in 1976 through Curiosity and Perseverance's sophisticated ongoing exploration today, represents an extraordinary, sustained scientific effort, one built patiently across decades, each mission carefully building upon the discoveries and lessons learned from those that came before it. Robot by robot, rover by rover, humanity has gradually transformed our understanding of Mars from distant speculation into detailed, evidence-based scientific knowledge, a transformation made possible only through this remarkable, ongoing collaborative effort spanning multiple generations of scientists and engineers. But the next explorers may not be robots. For over half a century, our exploration of Mars has been conducted entirely through the careful, patient work of robotic explorers, machines capable of surviving conditions that would prove instantly fatal to any unprotected human being. Yet for just as long, a parallel question has quietly persisted alongside this robotic exploration, growing more serious and more technically grounded with each passing decade. Could human beings themselves eventually travel to Mars, not merely to visit briefly, but to live there, perhaps even permanently? Answering this question requires confronting a series of formidable challenges, each connected directly to the very transformations we have explored throughout this documentary. The same collapsed magnetic field, thin atmosphere, and harsh climate that gradually transformed Mars from a warm, water-rich world into the cold desert it remains today. Perhaps the most serious of these challenges involves radiation exposure. As we explored several chapters ago, Mars lost its protective global magnetic field billions of years ago, leaving its surface almost entirely unshielded from harmful cosmic radiation arriving from deep space, along with periodic bursts of intense radiation released directly from the Sun itself. Here on Earth, our planet's magnetic field, combined with our considerably thicker atmosphere, provides substantial protection from this radiation, shielding all life on the surface from exposure levels that would otherwise prove seriously harmful over extended periods of time. Mars offers no such comprehensive protection, meaning that any human beings living on the Martian surface would face significantly elevated radiation exposure, a serious long-term health concern requiring careful mitigation through specially designed habitats, protective shielding, or, as we explored in an earlier chapter, potentially even natural shelter provided by the planet's ancient underground lava tubes. Beyond radiation, Mars's notably weaker gravity, roughly 38% as strong as Earth's own gravitational pull, presents an additional significant challenge for any long-term human presence. Extended periods spent within reduced gravity environments are already well understood through decades of research conducted aboard the International Space Station to cause measurable muscle atrophy and bone density loss among astronauts, effects that current exercise regimens can only partially mitigate. While scientists do not yet fully understand exactly how the human body would adapt to Mars's specific gravitational conditions across months or years of continuous exposure, current evidence strongly suggests that any long-term Martian settlement would need to carefully address this challenge, potentially through dedicated exercise routines, specialized equipment, or other countermeasures not yet fully developed or tested. Food production represents another substantial obstacle facing any long-term human presence on Mars. With the planet's thin atmosphere, harsh radiation exposure, and Martian soil containing perchlorate compounds toxic to humans in significant concentrations, growing food directly within unprotected Martian soil would prove impossible without significant remediation and protective infrastructure. Any realistic long-term settlement would likely require carefully controlled, enclosed growing environments, greenhouses specifically engineered to filter harmful radiation, regulate temperature and pressure, and provide plants with soil or growing medium free from the toxic compounds naturally present within unmodified Martian regolith. Given these substantial environmental challenges, any realistic human presence on Mars would necessarily depend on carefully engineered habitats, specifically designed to provide protection from radiation, maintain stable internal pressure and temperature, and create a genuinely livable environment capable of supporting human life across extended periods, potentially including entire human lifetimes for those born and raised within such settlements. Some proposed habitat designs draw directly upon the discoveries we explored regarding Mars's underground lava tubes, envisioning future settlements constructed partially or entirely within these naturally shielded underground spaces, taking advantage of the substantial radiation protection already provided by meters of overlying volcanic rock. Beyond these carefully engineered habitats, some scientists and engineers have proposed considerably more ambitious long-term concepts, collectively referred to as terraforming, the theoretical process of deliberately transforming Mars's broader planetary environment to more closely resemble Earth's own conditions. Various terraforming concepts have been proposed over the decades, including ideas centered around deliberately releasing greenhouse gases currently trapped within Martian polar ice and surface rock, potentially warming the planet's climate significantly and thickening its atmosphere in the process, gradually working to reverse, at least partially, some aspects of the very transformation we explored throughout the earlier chapters of this documentary. However, most current scientific analysis suggests that fully terraforming Mars transforming it into a genuinely Earth-like world capable of supporting an unprotected human presence directly on its surface, likely remains far beyond our current or even near-future technological capabilities, if it remains achievable at all given the fundamental physical realities we explored regarding Mars's collapsed magnetic field. Without restoring some form of protective magnetic shielding, any artificially thickened Martian atmosphere would likely face the same gradual erosion from solar wind that originally stripped away the planet's ancient atmosphere billions of years ago, suggesting that any large-scale terraforming effort would require solving this fundamental magnetic field challenge as well, a problem of almost unimaginable scale and complexity given our current scientific and technological understanding. Given these substantial challenges, most current serious planning regarding future human presence on Mars focuses considerably more on smaller, carefully engineered settlements rather than full planetary terraforming, envisioning habitats and colonies specifically designed to create livable, protected environments within an otherwise harsh and largely unmodified Martian landscape. Several space agencies and private companies have outlined increasingly detailed plans for such settlements, generally involving an initial period of robotic infrastructure development, followed by carefully planned crewed missions specifically designed to establish and gradually expand a sustained human presence on the Martian surface. The timeline for such ambitious plans remains genuinely uncertain, dependent on continued advances across numerous different technological fields, including propulsion systems capable of significantly reducing the current multi-month journey time to Mars, radiation shielding technology capable of adequately protecting both travelers and eventual settlers, and reliable systems capable of producing food, water, and breathable oxygen directly from resources available on Mars itself, rather than requiring these essential supplies to be transported entirely from Earth at tremendous ongoing cost and logistical complexity. Despite these substantial remaining challenges, the fundamental question of whether humans could eventually establish a genuine, sustained presence on Mars appears to be a matter of engineering and technological development, rather than one of fundamental scientific impossibility. Unlike questions surrounding Mars's ancient past, which remain constrained by the historical record preserved, however imperfectly, within the planet's rocks and geological features, questions about future human settlement remain open, shaped by decisions, investments, and technological breakthroughs still very much ahead of us rather than firmly fixed within an unchangeable past. Even if humans arrive, Mars will never truly become Earth. For all that decades of orbital observation, rover exploration, and careful scientific analysis have revealed about Mars, the planet continues to present scientists with a series of genuine, unresolved puzzles, questions that remain open despite the enormous body of evidence already gathered across more than half a century of dedicated study. These mysteries serve as an important reminder that our understanding of Mars, however extensive, remains fundamentally incomplete. Perhaps the most intriguing of these unresolved puzzles involves the periodic detection of methane within Mars's thin atmosphere. On Earth, methane is produced overwhelmingly through biological processes, making its detection on Mars a matter of considerable scientific interest and ongoing debate. NASA's Curiosity rover has detected methane concentrations within Gale Crater that fluctuate in ways not yet fully explained, sometimes rising and falling on a seasonal basis, and occasionally spiking suddenly and unpredictably before fading away again just as quickly. While methane can also be produced entirely through non-biological geological processes, including certain types of chemical reactions between water and specific volcanic rock formations, the exact source of Mars's fluctuating methane remains genuinely uncertain, leaving open the tantalizing, though entirely unconfirmed, possibility that some form of biological activity, whether ancient and preserved or, more provocatively, still ongoing today, might be responsible for at least a portion of these curious atmospheric readings. Closely related to this methane mystery is the broader, ongoing question of underground water on Mars, extending beyond the ice deposits we explored in an earlier chapter. Certain radar measurements gathered by the Mars Express orbiter have hinted at the possible presence of small, isolated pockets of liquid water existing far beneath the planet's southern polar ice cap, kept in a liquid state despite the extreme cold through a combination of pressure and dissolved salts that lower water's typical freezing point. This interpretation remains genuinely contested within the scientific community, with some researchers proposing alternative explanations involving unusual subsurface mineral or ice formations rather than genuine liquid water. Confirming or refuting the presence of such deep, isolated liquid water reservoirs would carry significant implications, both for understanding Mars's current geological activity and for evaluating the planet's ongoing potential to support microbial life even today. Mars's ancient climate history similarly continues to generate significant scientific debate, particularly regarding exactly how warm the planet's early atmosphere truly needed to become in order to support the extensive river systems, lakes, and potential ocean we explored earlier in this documentary. Some climate models suggest that even Mars's early, considerably thicker atmosphere may not have been sufficient on its own to maintain the sustained warm conditions necessary to explain the extensive water-carved features observed across the planet's surface, leading some scientists to propose that early Mars may have experienced only brief, episodic warm periods, perhaps triggered by intense volcanic activity or occasional large asteroid impacts, rather than a single, continuously warm and wet climate persisting steadily across an extended period of the planet's early history. Resolving this ongoing debate remains an active area of research, requiring more detailed atmospheric modeling combined with continued geological evidence gathered directly from the Martian surface. Another persistent puzzle involves what scientists sometimes refer to as Mars's missing carbon problem. Given the substantial evidence suggesting that early Mars once possessed a considerably thicker atmosphere, one likely rich in carbon dioxide, scientists have worked to account for exactly where all of this ancient atmospheric carbon eventually went, as the planet's atmosphere thinned dramatically over its long history. While some of this carbon was likely lost directly to space through the same solar wind stripping process we explored several chapters ago, and some may remain trapped within surface rocks and polar ice, current measurements of both atmospheric carbon and carbon trapped within accessible surface deposits do not fully account for the total quantity scientists believe must have existed within Mars's ancient atmosphere, suggesting that significant reservoirs of this missing carbon may remain hidden somewhere still undiscovered, whether deep underground or in some other form not yet identified through current exploration methods. Mars also continues to display certain strange seasonal changes that remain only partially understood, including recurring dark streaks that periodically appear along certain steep slopes during the warmer Martian seasons, gradually fading again as temperatures cool. These features, known as recurring slope linea, were initially proposed by some scientists as possible evidence of seasonal briny water flows seeping temporarily down these slopes, though more recent analysis has raised significant questions about this original interpretation, with some researchers instead proposing that these streaks might result from the seasonal movement of fine, dry sand and dust rather than any actual liquid water. This ongoing scientific debate illustrates just how challenging it can be to definitively interpret certain Martian surface phenomena using only orbital imagery, without the benefit of direct, close-up examination by a rover positioned at the exact location in question. Beyond these specific puzzles, Mars continues to produce a steady stream of smaller, unexplained observations with each new mission and each new set of data gathered, whether from rovers analyzing rock samples directly, orbiters conducting increasingly detailed surface surveys, or following InSight's groundbreaking seismic work. Ongoing efforts to further refine our understanding of the planet's deep interior structure. Each new discovery, while adding valuable pieces to our broader understanding of Mars, frequently raises additional questions in turn, a pattern that has characterized Mars exploration since the earliest Viking missions nearly 5 decades ago, and shows little sign of slowing, as exploration efforts continue to expand and grow increasingly sophisticated. This persistent pattern, where each new discovery generates additional unanswered questions rather than providing simple, final resolution, reflects something genuinely important about the nature of Mars as a subject of ongoing scientific study. Mars is not a simple, fully solved puzzle, awaiting only a final missing piece. It is instead an active, evolving area of scientific investigation, one where our understanding continues to develop and refine itself gradually, shaped by each new mission, each new instrument, and each new generation of scientists bringing fresh perspectives and improved technology to bear on questions that, in some cases, have remained genuinely open since humanity's earliest telescopic observations of this distant, reddish world. Perhaps Mars's greatest lesson is not about the past, but about our future. We have now traveled the full arc of Mars's extraordinary story, from its violent birth within the same swirling disk of dust that gave rise to Earth, through its brief, remarkable period as a warmer, wetter world, into the slow, patient transformation that stripped away its magnetic field, its atmosphere, and ultimately its oceans, leaving behind the cold, red desert we observe today. Now, at the close of this journey, it is worth stepping back to consider the deeper question that has quietly shaped every chapter of this documentary. Why did Mars and Earth, born from such similar beginnings, arrive at such profoundly different destinies? The answer, as we have seen throughout this exploration, does not lie in any single dramatic event, but rather in a series of small, compounding differences, each one seemingly modest on its own, yet collectively decisive in shaping the fate of an entire planet. Mars's smaller size meant a smaller core, which cooled more quickly, which led to an earlier loss of its protective magnetic field. This magnetic field loss exposed its atmosphere to the relentless erosion of the solar wind, gradually thinning that atmosphere across hundreds of millions of years. This thinning atmosphere, in turn, caused temperatures to fall and pressure to drop below the threshold required for liquid water to remain stable, triggering the final transformation from a once water-rich world into the dry, frozen desert now familiar to us. Earth, meanwhile, avoided this same fate largely due to its considerably greater size and mass, factors that allowed our planet's core to remain molten and active for over 4 billion years, continuously generating the protective magnetic field that continues shielding our atmosphere, and by extension, all life on Earth to this very day. This single difference in scale, seemingly modest in the broader context of planetary formation, ultimately determined whether a planet retained the water and atmosphere necessary to sustain complex, thriving life across billions of years, or gradually lost those same essential qualities, becoming instead a quiet, frozen monument to what might have been. This realization carries profound implications that extend well beyond our own solar system. As astronomers continue discovering thousands of planets orbiting distant stars throughout our galaxy, many roughly comparable in size to Earth and Mars, positioned at varying distances from their host stars, Mars's history offers an essential and sobering lesson. Planet size, its distance from its star, and its position within a star's theoretical habitable zone, while certainly important, do not alone guarantee lasting habitability. A planet must also possess sufficient internal mass and heat to sustain a protective magnetic field across billions of years, a factor considerably more difficult to detect or confirm from the vast distances separating us from these newly discovered worlds. This understanding has become increasingly central to how scientists evaluate the genuine habitability potential of exoplanets discovered throughout the galaxy, adding an essential layer of consideration beyond simply calculating whether a given planet orbits within the right distance from its star to theoretically support liquid water. Mars serves as a powerful, nearby reminder that habitability is not a simple, binary quality determined by distance alone, but rather a delicate, ongoing balance requiring multiple factors to align correctly and to remain aligned across enormous spans of geological time. Perhaps most significantly, Mars offers humanity a uniquely valuable perspective on Earth's own fragility, one unavailable through the study of any other planet in our solar system. Venus, though similar in size to Earth, followed an entirely different path toward its own extreme, uninhabitable conditions, offering a valuable but very different kind of cautionary comparison. Mars, by contrast, followed a path remarkably similar to Earth's own early history for a significant portion of its formative years, only to ultimately diverge due to differences that, while significant, remain considerably more subtle and instructive than the extreme greenhouse transformation experienced by Venus. Studying Mars, then, is not simply an exercise in understanding a distant, dead world. It is, in a very real sense, an exercise in understanding the delicate, ongoing conditions that continue to make life on Earth possible, conditions we often take entirely for granted precisely because they have remained stable across the entire span of human history, and indeed, across the entire history of complex life on our planet. Mars quietly reminds us that this stability, however permanent and reliable it may feel, is not guaranteed indefinitely, nor was it ever inevitable from the earliest moments of planetary formation. This lesson extends naturally into humanity's own future, both in terms of our responsibility toward protecting Earth's continued habitability and in terms of our growing ambitions to eventually establish a human presence on Mars itself. Should humanity eventually succeed in establishing permanent settlements on the Martian surface, whether within specially engineered habitats or, as some have proposed, deep within the planet's ancient lava tubes, we will be doing so not upon a second Earth, but upon a fundamentally different world, one that lost its own opportunity for lasting habitability billions of years before humanity ever evolved to look up and wonder about it. And yet there remains something deeply hopeful within Mars's long, complex story as well. Despite losing its water, its thick atmosphere, and its magnetic field, Mars did not become entirely inert or lifeless in a broader sense. Its volcanoes continued erupting for billions of years after its oceans first began to disappear. Its interior continued generating detectable seismic activity, as InSight's careful listening ultimately confirmed. Ice remains preserved just beneath its surface, and organic molecules, the essential building blocks of life as we understand it, remain preserved within its ancient rock, patiently awaiting the kind of detailed scientific analysis that missions like Mars Sample Return may eventually provide. In this sense, Mars remains a planet still capable of teaching us, still capable of revealing new insights with each careful mission and each new generation of scientific instruments sent to study it more closely. Its story is not simply one of loss and transformation, but also one of remarkable preservation. A planet whose cold, dry, geologically quiet conditions have inadvertently protected billions of years of geological and potentially biological history, preserved in a way that Earth's own active, ever-changing surface could never have managed to achieve across the same immense span of time. Today, Mars is a quiet world of red deserts, frozen valleys, and silent mountains. But every canyon, every dry riverbed, and every grain of rust-colored dust tells the story of a planet that once had the ingredients for something extraordinary. Perhaps the greatest mystery is not why Mars became a desert, but why Earth did not, and somewhere within that answer may lie the story of our own future. High above the silent deserts of Mars drift two tiny moons unlike any others in the solar system. They are misshapen, mysterious, and slowly writing the next chapter of Mars's story. Unlike Earth's moon, a single, large, gracefully rounded companion that has shaped tides, calendars, and human imagination for as long as our species has existed, Mars is orbited by two remarkably small, irregularly shaped moons, so modest in size that they remained entirely undetected until relatively recently in the history of astronomy. These two moons, named Phobos and Deimos, orbit so close to the Martian surface and reflect so little sunlight due to their dark, carbon-rich composition that they proved extraordinarily difficult to spot even after telescopes had become powerful enough to reveal considerable detail across the rest of the Martian surface. It was not until 1877 that American astronomer Asaph Hall, working through a period of considerable frustration and repeated failed attempts at the United States Naval Observatory, finally succeeded in identifying both of these elusive moons within just a few days of one another. Hall named them Phobos and Deimos, drawing from Greek mythology, where these two figures represented fear and dread respectively, fitting companions for a planet already named after the god of war. This naming choice reflected the mythological tradition already well established for Mars itself, extending the same thematic language to the newly discovered moons orbiting closely around it. From the very first detailed observations, both Phobos and Deimos revealed themselves as strikingly different from most other moons found throughout the solar system. Rather than the smooth, roughly spherical shape typical of larger moons, including Earth's own, Phobos and Deimos appeared distinctly irregular and lumpy, more closely resembling asteroids than traditional moons, an appearance that immediately raised intriguing questions about their true origin. This asteroid-like appearance is not merely a coincidence. Both moons are relatively small, Phobos measuring only about 22 kilometers across at its widest point, while Deimos measures roughly half that size, dimensions considerably smaller than what would typically be required for a moon's own gravity to pull it into the smooth, rounded shape characteristic of larger celestial bodies. Their surfaces, heavily cratered and composed of dark, carbon-rich material, closely resemble the composition and appearance of certain asteroids found within the nearby asteroid belt, positioned between the orbits of Mars and Jupiter. For decades, this resemblance led many scientists to favor a capture theory, the idea that Phobos and Deimos did not form naturally alongside Mars at all, but instead originated as ordinary asteroids that wandered too close to the planet at some point in the distant past, becoming gradually captured by Mars's gravity and pulled into the close, stable orbits we observe today, in a process broadly similar to the theorized capture of Neptune's moon Triton that we explored in our previous documentary. However, this capture theory faces certain significant challenges when examined closely, particularly regarding the precise, nearly circular orbits both moons currently maintain, positioned almost directly above the Martian equator. Objects captured through gravitational interaction typically settle into far more irregular, elongated orbits, at least initially, making the remarkably clean, stable orbits of Phobos and Deimos somewhat difficult to fully explain through simple capture alone, without invoking some additional process to have gradually smoothed their orbital paths into the neat configuration observed today. This difficulty has led some scientists to propose an entirely alternative formation theory, suggesting that Phobos and Deimos may have instead formed directly around Mars, condensing from debris thrown into orbit following a massive ancient impact between Mars and another large object early in the planet's history, a process broadly similar to the leading theory explaining the formation of Earth's own moon. Under this theory, the asteroid-like appearance of both moons would result not from an outside origin, but simply from their small size and the composition of debris available within the impact-generated disk from which they formed. Resolving this ongoing debate between capture and impact formation theories remains one of the more compelling open questions surrounding the Martian system, one that scientists hope future missions may eventually help settle through more detailed, direct examination of these two small companions. Among the most curious features observed on either moon are the strange, parallel grooves that stretch across significant portions of Phobos' surface, a network of shallow linear trenches that has puzzled scientists since they were first clearly photographed by orbital spacecraft. Several competing explanations have been proposed for the origin of these grooves, including the possibility that they represent stress fractures caused by the immense tidal forces exerted by Mars's gravity as it slowly pulls Phobos closer with each passing orbit, or alternatively, that they may have formed as a chain of secondary impacts, debris ejected from a large impact crater elsewhere on the moon's surface, falling back down and carving these parallel lines as it struck the ground at a shallow angle. This mention of Phobos gradually being pulled closer to Mars points toward one of the most remarkable and well-documented aspects of this small moon's ongoing story. Unlike most moons throughout the solar system, which either maintain stable orbits or very gradually drift farther away from their host planet over time, Phobos is doing precisely the opposite, spiraling slowly but measurably closer to Mars with each orbit, drawn inward by the same tidal forces responsible for those mysterious surface grooves. Current calculations suggest that Phobos moves approximately 2 meters closer to Mars every 100 years, a seemingly modest rate that nonetheless places the Moon on a genuinely inevitable collision course with its host planet, projected to occur within the next 30 to 50 million years. Rather than crashing directly into the Martian surface intact, scientists generally believe that Mars's steadily strengthening tidal forces will eventually tear Phobos apart entirely as it draws closer. Its own gravity no longer sufficient to hold the Moon together against the increasing gravitational strain, likely scattering its remains into a temporary ring system encircling Mars, not unlike the eventual fate predicted for Neptune's moon Triton across a considerably longer cosmic timescale. Deimos, by contrast, tells a notably different story. Positioned considerably farther from Mars than Phobos, Deimos experiences much weaker tidal forces, and rather than spiraling inward toward eventual destruction, current evidence suggests it is instead very gradually drifting farther away from Mars, following a pattern more typical of moons found throughout the rest of the solar system. Deimos also appears smoother than Phobos, lacking the same distinctive network of grooves, and displays a notably different pattern of surface cratering, differences that continue to inform the broader scientific debate regarding whether both moons truly share a common origin, or instead arrived at their current orbits through somewhat different histories. Given their relatively close proximity to Mars and their modest gravitational pull, considerably weaker than that of Mars itself, both Phobos and Deimos have attracted growing interest as potential targets for future exploration missions, including Japan's planned Martian Moons exploration mission. Designed specifically to visit Phobos, collect a physical surface sample, and return that sample to Earth for detailed laboratory analysis, an effort that could finally help resolve the long-standing question of whether these moons originated as captured asteroids or formed directly alongside Mars itself. Some mission planners have also proposed that Phobos, given its modest gravity and relatively close orbit, could eventually serve as a valuable staging point for future human missions to the Martian surface, offering a stable location from which astronauts could operate remotely controlled equipment on Mars below, while avoiding some of the greater technical challenges associated with landing and later launching directly from the planet's surface itself. Studying these two small, unusual moons offers scientists valuable insight, extending well beyond their own individual history, providing additional clues about the broader environment surrounding Mars during the earliest, most chaotic periods of the planet's formation, an era we explored in considerable detail earlier in this documentary. Whether ultimately confirmed as captured asteroids or debris from an ancient impact, Phobos and Deimos remain living evidence of the same turbulent processes that shaped the entire Martian system so long ago, small, quiet witnesses continuing to orbit patiently overhead, even as the planet below them was gradually transforming from a warm, water-rich world into the cold desert it remains today. But Mars doesn't only surprise us in orbit. Sometimes it surprises us from the sky itself. Imagine a storm so enormous that it hides an entire planet for months. On Mars, this isn't science fiction, it's part of the weather. To understand how such an extraordinary event becomes possible, we first need to appreciate just how different Martian weather truly is from anything experienced here on Earth. Mars possesses an atmosphere only about 1% as dense as Earth's own, a thin, fragile envelope of gas composed primarily of carbon dioxide, with only trace amounts of nitrogen, argon, and oxygen mixed throughout. This remarkably thin atmosphere means that Martian weather, while genuinely dynamic and occasionally dramatic, operates according to fundamentally different physical rules than the weather systems we experience here on Earth. Despite its thinness, Mars's atmosphere remains more than capable of generating significant wind, particularly given the planet's considerable daily and seasonal temperature swings. Because Mars lacks the thick atmospheric insulation that helps moderate temperature extremes here on Earth, its surface temperature can vary dramatically between day and night, sometimes swinging by more than 50 degrees Celsius within a single Martian day. These sharp temperature differences, particularly pronounced between sunlit and shadowed regions, generate persistent pressure differences across the planet's surface, driving winds that, despite moving through such thin air, remain capable of lifting significant quantities of the fine, powdery dust that covers much of the Martian surface. This fine Martian dust, composed largely of iron oxide, the same compound responsible for the planet's distinctive rust-colored appearance that we explored earlier in this documentary, proves particularly easy for even modest winds to lift and carry, given how remarkably small and lightweight individual dust particles tend to be. Under normal conditions, these winds generate relatively modest, localized dust storms, similar in scale and behavior to dust storms that occasionally occur within Earth's own desert regions, kicking up visible clouds of dust that typically remain confined to a relatively limited area before gradually settling back down to the surface within a matter of days. However, during certain periods, particularly when Mars approaches its closest point to the Sun within its elliptical orbit, a period when the planet receives notably more solar heating than usual, these relatively modest, localized dust storms occasionally begin to grow in a way that proves genuinely remarkable, expanding rapidly beyond their initial boundaries and eventually merging together into storm systems capable of encircling significant portions of the entire planet. Scientists still do not fully understand every detail regarding exactly how these smaller, localized storms occasionally escalate into truly global events, though current understanding points toward a self-reinforcing feedback process playing a significant role. As dust lifts into the thin Martian atmosphere, these suspended particles absorb sunlight considerably more efficiently than the surrounding clear air, causing the dust-filled atmosphere to warm noticeably compared to adjacent regions. This localized atmospheric warming generates additional wind, which in turn lifts even more dust into the atmosphere, gradually expanding the storm's overall size and intensity in a compounding cycle that can, under the right conditions, continue building for weeks at a time. An additional, genuinely fascinating characteristic of these Martian dust storms involves the electrical charge that frequently builds up within the suspended dust itself. As countless individual dust particles collide repeatedly with one another while suspended and swirling within the atmosphere, friction between these particles generates significant static electrical charge, similar in basic principle to the static electricity generated when rubbing certain materials together here on Earth. This electrified dust has been directly detected by several Mars missions, and some scientists suspect it may even occasionally generate visible electrical discharges, though this phenomenon remains an area of ongoing scientific investigation rather than a fully confirmed characteristic of Martian storms. Beyond their sheer visual scale, these massive dust storms carry genuinely significant consequences for the broader Martian environment while they persist. Global dust storms can measurably alter surface temperatures across the planet, since the thick suspended dust both blocks a portion of incoming sunlight from reaching the surface directly, while simultaneously trapping a small amount of additional heat within the lower atmosphere, creating temperature effects that ripple outward and influence broader atmospheric circulation patterns for as long as the storm persists, sometimes for several months at a time before conditions finally begin to settle. These extended global storms also pose a genuinely serious practical challenge for robotic exploration, a challenge that became devastatingly clear during the final chapter of the Opportunity rover's remarkable, nearly 15-year mission, which we explored briefly in an earlier chapter of this documentary. In June of 2018, a massive global dust storm began spreading rapidly across the Martian surface, eventually growing large enough to completely encircle the entire planet, blocking so much sunlight that Opportunity's solar panels, its sole source of electrical power, could no longer generate sufficient energy to keep the rover's critical systems operating. As the storm intensified and sunlight continued to dim across Opportunity's location, mission engineers on Earth watched with growing concern as the rover's power levels steadily declined, eventually forcing Opportunity into a low-power hibernation mode designed to protect its most critical systems while conserving whatever remaining energy the rover could still generate. Mission controllers continued attempting to re-establish contact for months after the storm eventually began to clear, sending repeated commands and listening carefully for any response. Unfortunately, Opportunity never responded again, its batteries likely damaged beyond recovery by the storm's unprecedented duration, or its critical internal components too cold, deprived of the electrical heating power normally used to protect them through the frigid Martian nights. In February of 2019, NASA formally declared Opportunity's historic mission complete, bringing an emotional conclusion to a rover that had operated nearly 60 times longer than its original planned 90-day mission. This dramatic conclusion to Opportunity's mission highlights a genuinely serious consideration for any future human presence on Mars as well, a topic connected directly to our earlier exploration of the practical challenges facing potential Martian settlement. Any future human habitat established on the Martian surface would need to account carefully for the possibility of extended global dust storms, ensuring sufficient backup power generation, likely through nuclear rather than solar sources, capable of maintaining critical life support systems even during the months-long periods when a global storm might significantly reduce available sunlight across the entire planet. Beyond power generation concerns, these massive dust storms would also present other significant challenges for future human explorers, including reduced visibility potentially complicating outdoor operations, and the accumulation of fine dust particles on equipment, solar panels, and habitat exteriors, a persistent maintenance challenge that mission planners continue studying carefully as they refine their broader plans for eventual human exploration of the Martian surface. Despite decades of study, including extensive orbital monitoring, specifically designed to track and better understand these massive storm systems, scientists still cannot reliably predict exactly when a given Martian dust storm season might produce a genuinely global event, versus simply a series of smaller, more localized storms that never manage to fully merge and encircle the planet. This remaining uncertainty reflects, once again, a pattern we have encountered repeatedly throughout this documentary, a planet that, despite extensive study across decades of dedicated exploration, continues to reveal new layers of complexity with each fresh observation, resisting any simple, fully complete understanding. Yet even after decades of exploration, Mars still refuses to give us all of its answers. One day, the first human footprints may press into the red dust of Mars, but what happens after that? For over half a century, our exploration of Mars has unfolded entirely through robotic proxies, careful machines capable of enduring conditions no unprotected human body could survive. Yet across recent decades, this exploration has increasingly been shaped by a parallel and increasingly serious ambition, one moving steadily from speculative fiction toward genuine, technically grounded mission planning. Multiple space agencies and private companies now maintain active, detailed plans specifically aimed at eventually sending human beings to the Martian surface, not merely for a brief historic visit, but as the foundation for a sustained, long-term human presence. NASA's long-term approach to eventual human Mars exploration has developed gradually across several decades, evolving through numerous studies and mission concepts, generally organized around a step-by-step strategy that begins closer to home before gradually extending outward. This approach has typically emphasized establishing sustained operations on and around the Moon first, using this closer, more easily reached destination as a proving ground for testing critical technologies, life support systems, and operational procedures that would later prove essential for the considerably longer and more logistically demanding journey to Mars itself. Alongside NASA's institutional approach, private aerospace companies have increasingly become significant players in shaping the practical timeline toward eventual human Mars exploration, with SpaceX's ambitious Starship program representing perhaps the most publicly prominent example. Designed as a fully reusable spacecraft system capable of carrying substantial cargo and eventually human crews toward Mars, Starship represents a fundamentally different approach toward reducing the enormous cost historically associated with deep space missions. an essential consideration given the enormous scale of any realistic effort to establish a genuine, sustained human presence on another planet. Regardless of which specific organization or mission architecture ultimately succeeds in landing the first human beings on Mars, any realistic long-term settlement would face the same fundamental engineering challenges we explored in earlier chapters of this documentary. Challenges rooted directly in the same planetary transformation that reshaped Mars from a warm, water-rich world into the cold, thin-atmosphered desert it remains today. Constructing the very first sustained human habitat on Mars would likely represent one of the most technically demanding engineering achievements in human history, requiring structures specifically designed to maintain stable internal pressure and temperature, while simultaneously providing adequate protection from the harmful radiation exposure resulting from Mars's long-lost magnetic field. Some current mission concepts propose an initial period of robotic construction, where automated systems arrive ahead of any human crew, beginning essential habitat construction, and potentially even utilizing Martian regolith itself as a raw building material through specialized three-dimensional printing techniques currently under active development and testing here on Earth. Among the most critical technical challenges facing any sustained Martian settlement involves reliably producing breathable oxygen directly from local Martian resources, rather than requiring this essential resource to be transported entirely from Earth at tremendous ongoing cost. NASA's Perseverance rover, which we explored in considerable detail in earlier chapters regarding its search for ancient biosignatures, also carried a dedicated experimental instrument called MOXIE, specifically designed to test technology capable of converting Mars's abundant atmospheric carbon dioxide directly into breathable oxygen. This technology demonstration succeeded in producing meaningful quantities of oxygen directly from the Martian atmosphere, offering an important proof of concept for technology that future, considerably larger-scale systems could eventually build upon to help support sustained human habitation. Growing food reliably on Mars presents an equally significant challenge, one we touched upon briefly in our earlier chapter, examining the broader feasibility of human Martian settlement. Given the toxic perchlorate compounds naturally present within unmodified Martian soil, alongside the planet's harsh radiation exposure and thin atmosphere, any realistic food production system would necessarily require carefully controlled, enclosed growing environments. Specifically engineered greenhouses capable of filtering harmful radiation, while providing plants with either specially treated Martian soil or an entirely separate, artificially created growing medium free from the toxic compounds found naturally within the surrounding Martian regolith. Water, an equally fundamental resource for any sustained human presence, would most likely be sourced directly from the underground ice deposits we explored in an earlier chapter, rather than transported from Earth at prohibitive cost across such enormous distances. Current mission planning increasingly emphasizes identifying and eventually establishing settlements near locations with confirmed, easily accessible underground ice, allowing future settlers to extract and purify this ancient, preserved water for drinking. Agriculture, and through appropriate chemical processing, potentially even breathable oxygen production, effectively transforming these frozen remnants of Mars's ancient waterage past into an essential resource supporting its future human inhabitants. Beyond these substantial technical and logistical challenges, any long-term Martian settlement would also need to seriously address the significant health considerations we explored previously, including sustained radiation exposure and Mars's notably weaker gravity. Factors that current scientific understanding suggests could meaningfully affect human health across extended periods of habitation, particularly regarding any future generations potentially born and raised entirely within the Martian environment, rather than having first developed within Earth's own considerably stronger gravitational field. Given these substantial remaining challenges, it becomes worth revisiting the broader concept of terraforming, deliberately transforming Mars's planetary environment to more closely resemble Earth's own conditions, a concept we explored briefly in an earlier chapter. While terraforming remains an enduringly popular concept within science fiction, current scientific analysis continues to suggest that fully terraforming Mars into a genuinely Earth-like world remains far beyond our current or near-future technological capabilities. Particularly given the fundamental challenge posed by Mars's long-lost magnetic field, a factor that would likely cause any artificially thickened atmosphere to gradually erode away through the same solar wind stripping process that originally transformed the planet billions of years ago. This distinction between genuine scientific possibility and popular science fiction imagination remains an important one to maintain clearly, particularly as public interest in eventual Mars settlement continues growing. While establishing small, carefully engineered human settlements on Mars appears increasingly achievable within coming decades, given continued technological development across the numerous fields we have explored throughout this chapter. Transforming the entire planet into a genuinely Earth-like world capable of supporting an unprotected human presence directly across its surface remains, at least based on current scientific understanding, a possibility positioned much further into a distant, uncertain future, if it remains achievable at all. Could Mars ever become Earth again, in the sense its earliest, warmest history might suggest it once resembled? Perhaps, though only across a timescale, and through a technological capability considerably beyond anything currently within humanity's reach. What remains far more immediately achievable, and increasingly the focus of current mission planning across numerous space agencies and private companies alike, is the establishment of smaller, carefully protected human settlements, quiet outposts of Earth life extending humanity's presence to a second world for the very first time in our species' long history. Throughout this documentary, we have traced Mars's complete story, from its violent shared birth alongside Earth billions of years ago, through its brief, remarkable period as a warmer, water-rich world, into its slow transformation into the cold desert we recognize today. And finally toward humanity's own growing ambitions to eventually return, not merely to observe from orbit or explore through robotic proxies, but to live there directly, carrying Earth's own life to a second planetary home for the first time in our species' long, patient history. Mars reminds us that planets, like civilizations, can change beyond recognition. It was once warmer, wetter, and perhaps even capable of supporting life. Today it stands as a silent monument to the delicate balance that makes Earth so rare. As we continue reaching toward the red planet, we aren't just exploring another world, we're learning how precious our own truly is. And perhaps, somewhere beneath the red dust, Mars is still waiting to tell us one final story.